This is the experiment you already saw. We have a magnet, a power supply. What we know for sure is that current is just a set of particles traveling in the same direction. So if we have particles traveling in the same direction, it's supposed to be a force acting on the wire with the current. And now we can apply the right-hand rule to figure out the direction of that force. Plus, minus, well, electrons travel like this. We could apply left-hand rule for electrons, but fictional positive particles travel like that. We can apply right-hand rule to those fictional particles. So north-south magnetic field like this, velocity of positive particles like that. The force points up, and that force makes this wire move. What we didn't know yet is how would we calculate the magnitude of this force. It's easy. We just have to multiply the force acting on one charge by a number of charges. And in that case, the expression for the force acting for magnetic field on a wire with a current turns out to be this. It's proportional to current, magnetic field of course, the length of a part of a wire, which is a magnetic field. The wire might be very long, but only a small part inside the magnetic field. So magnetic field doesn't act on the part outside it. And of course, the angle. If you have a wire which is parallel to magnetic field lines, in that case there is no force acting on the wire. Wire is supposed to have some angle toward magnetic field. In that case, the force is equal to this. Right-hand rule works. I'm not going to ask you this question. If this is a magnetic field, well, current by definition always points in the direction of positive charges. So there is no left-hand rule for currents. Left hand only for negative charges. For current, we just use right hand always. Finger points in the direction of the current. These three fingers point in the direction of the magnetic field. The thumb shows the force. In this situation, it's supposed to point to the left. And we can ask, what if the wire is kind of bent and have some shape? Well, that's one possible situation, the easiest one. We bend it with 90 degrees angle. To calculate the net force acting on a wire like that, what do? We have to calculate force acting on one part, net force acting on the second part, and add them up together. Turns out that the net force acting on a wire like this equals the force acting on a straight wire with the same current connecting, well, beginning and the end. And even if your field has a different direction, as long as it's uniform, the rule works. Again, if you calculate the net force acting on this bent wire, the result is the same as for the force acting on this wire. Straight wire connecting beginning and the end. Very useful fact. Now I want to ask you a question. What do you think about this situation? We just said wires number 1 and wires number 2 experience the same net force. What about the wire number 3? Which is not just angled. So which of these 3 wires experiences more force? And of course we have only 4 possible answers. And of course we just said wires 1 and 2 experience the same force, so don't press 1 or don't press 2. So your choice is narrowed down to button number 3 and button number 4. Right? What did you press? 3 or 4? Good, thank you. Finally, someone smiling besides me.
All right. Of course, we just basically said already the shape doesn't matter. We can just connect beginning of a wire and end and calculate the net force acting on that straight wire. Why it doesn't matter? Because of wire of any shape, we always can break down in small parts. Some of those parts parallel to the field and don't experience any force. Some of those parts perpendicular to the field, but for these two parts, forces pointing up in the direction we cancel out, so only these parts important, which is this, and this part is the same for any kind of shapes, you know. So, what do you think about this kind of wire? It's a loop. So, what's your take on this question? Well, seconds, just. What is a loop? Well, it's a wire which starts and ends in the same place. So, of course, on one hand, we would calculate 4 forces, different forces acting on each part of a loop. However, we get all forces cancel out each other because, for example, this pair of forces, same length, opposite direction, cancel out. These pair of forces, same length, opposite direction, cancel out. So the net force acting on this loop is 0. Or we could say the loop starts here and ends here. So the force acting on this loop must be equal to the net force acting on a straight wire, which ends here and begins here. But that wire doesn't have any length, it's just a dot. So there is no force acting on a wire like that. What about this one? Again, we just said, shape doesn't matter. Even for this wire, the net force is supposed to be equal to 0. And what is important is that all questions about wire and loop and force has been related to a uniform magnetic field. That's important. You see, magnetic field lines spread evenly everywhere. So magnetic field is the same in magnitude and direction everywhere. If magnetic field is not uniform, in that case, net force acting on the loop might not be equal to 0 and requires direct calculation. Well, there are 2 other situations to discuss quickly. What if only a part of a loop is in the magnetic field? Well, in this situation, this part of the loop is outside magnetic field. There is no force acting on it. We just can cut it up and forget about it. So, only this part of the loop is in the magnetic field, and this to us. Now it's just a bent wire. And we just said, for a wire like that, the net force acting on it equals the net force acting on a straight wire, which connects beginning and the end. That's it. What about this situation?
Well, here again, the part outside of the field doesn't matter. So it's just a regular bent wire. We can replace it with a straight wire like that and calculate the net force acting on this part of the loop. That's it. That's how it works. Of course, you can prove this fact mathematically by calculating the forces, but in the end, you get exactly the same result. You can replace any wire in the uniform magnetic field with a straight wire. Now, this is supposed to be one of the handouts, and what I want you to do is to calculate the net torque acting on this wire and this magnetic field. Okay? It probably should take a minute or two for you. And I will spend this time to prepare to another demonstration. This, what you see, is exactly the same situation. A loop. Well, to create magnetic field, all I have to do is bring the magnet close to it. So, why do we need to talk about net torque? Because we just said net force is 0. However, well, what I have here is a simple 9-volt battery. And this is a simple bar magnet, north, south. So I can bring this magnet close to this single loop, and I can connect the batteries with it. Like this. Oops. You see, when I touch it, it moves a little bit. It moves. Well, if I want to make this motion more consistent, I just have to replace this magnet with a stronger magnet. Like this. And now, see? It moves again. As long as there's a current through the loop, it starts moving. What kind of motion does it make? It's a rotational motion. How do we explain the rotational motion? There is torque acting on a number. That's it. And this is a simple motor, and we use motors everywhere. So if you want to understand how it works, we need to know how to calculate the torque acting on the loop. So, well, what do we do? Well, first of all, we need to remember how to calculate torque in general. This is the expression for the force acting on a wire with a current and magnetic field. What is the definition of torque? Who remembers? I'm not going to ask the definition. If you remember, just raise your hand. No comments. Well, torque equals force times lever arm. Lever arm is the shortest distance from the axis of rotation to the point of application of a force. And in this situation, well, again, if you remember, we can choose axis of rotation anywhere, but the physical action of rotation in my experiment is here, and the loop rotates about that axis. So, let's say this side of the loop. The current travels up, magnetic field points to the right, so current, field, the force acting on this part of the loop points straight down. We reverse the direction of the current, we reverse the direction of the force. That's why this side, if we look at it from above, that's a top view. This side, B, whatever, this side moves away from me, and this side, when I look at it from the top, moves towards me. So this loop rotates like this. What about these two sides? Do they experience any force? Yes, of course. However, those forces, actually no. Current is anti-parallel or parallel to the field. The angle between field and current is 0 or 180. There's no force. How do we calculate torque? Total torque? Well, we just have to add two torques together. And in this situation, the result is simple. The straightforward calculation says that the net torque acting on this loop in a magnetic field equals this. I represents the current in the loop, B represents magnetic field, A represents the area of this loop. And if we look at this expression now, the shape doesn't matter anymore, only area matters. So you can get a circular loop, a triangular loop, or whatever shape loop is, as long as the area, current, and the magnetic field is the same, the torque acting on the loop has the same magnitude. However, there is another variable torque depends upon, the angle. Well, angle matters because here, if your loop now has a different orientation relative to the magnetic field, the lever arm for the force is different now. So this is the line of action for the force, that's the axis. And now, the distance from the axis to the line of action, lever arm, is shorter. So now the torque is supposed to have a smaller value. So if we carry out the direct calculation, that gives finally the expression for the total torque acting in the loop and magnetic field. Now, in addition to current, area, and magnetic field, we also have to use a specific angle. What kind of angle? Again, that's a point of a common misconception. If this is a magnetic field, and this is a loop, but now it's not a top view, like this. It's a side view. That's how we see the loop if we look from a side. Basically, all we see is just one wire. So the current here in this loop might be traveling, well, in this wire, up, then it goes down, then it goes back again, and here it goes up. So, if you look at this picture, you want to use this angle. It's a natural intention. That would be wrong. Because by definition of the torque, if you write the expression I, A, B, sine theta, this angle must be measured between the magnetic field and between the normal to the loop. This line, this vector, is perpendicular to the loop, and this is the angle theta we must use here. Just remember that. And, well, I want to ask you this question. That's probably the last personal response question for today. Here, what you see are several loops with the same current, same area, in the same magnetic field. The only difference is the orientation. You also can see that vector which is perpendicular to the loop. It has several names. We call it a normal, like normal force because it's perpendicular. Or also for the loop, we call it area vector. Again, by definition, the length of this arrow is supposed to be equal to the area of the loop. That's why we call it area. So large loop, large area, longer area vector. Small loop, smaller area, shorter area vector. But for this question, area is not important. It's the same for all loops. What's important is the orientation. You also could remember my experiment. In my experiment, the loop is horizontal and magnetic field lines are horizontal. And this orientation, number 4. All right. So let me get 3, right? Let's see. So this orientation gives the angle of 90 degrees, and sine of 90 degrees equals what? Exactly. We need to know that. So, can a value of sine be greater than 1? No. That's the maximum value of the sine. That means for this orientation, torque has the maximum possible value. When the loop itself is parallel to the magnetic field, the torque reaches its maximum. That's it. And now, for any other orientation, torque decreases. And it goes to 0 in the situation when the angle between the field and area vector is 0 and sine of 0 is 0. Well, so the maximum, 0. This is closer to the maximum. This is closer to 0. Right? Yes. So what does it give us? It's supposed to be either B or C because it starts from 4 and it ends with 2. You see, we can have a multiple choice question. You don't even have to sometimes analyze everything. You can analyze just parts of the question. This is the only one that fits. It saves you microseconds, maybe milliseconds, but sometimes it's important. All right. See. And 6 more minutes. The last handout. It's basically exactly the same problem, but wording is a little bit more confusing. That's it. So if you read the problem, you have a loop, and BC side starts moving away from you. So what does it tell us about? Well, first of all, this is the side BC. When you release the loop from rest, and this side starts moving away from you, so it moves down. That means the force acting on the loop, on this part of the loop, points down. That means the force acting on this part of the loop points up. So this is how it starts moving. And now, what does it tell us about magnetic field? Well, magnetic field is related by the right-hand rule to the direction of the current force. So, current magnetic field points to the right. That's the first fact you may want to use. The magnetic field, now we have to say, points in the direction of positive x axis. Well, side view. Which side? A, B. So if your eye now is here, you're looking like that. This is the side you see. So you have to turn it around in your mind. The magnetic field still points in the same direction. Well, and now you can answer many different questions. For example, what about the force? What is happening to the force? Well, if you turn it around like this, right force acting on BC will be turning down. So this force points down, this force points up. And again, just to check, we can use the right-hand rule. Current, field, force. Now we know, relative to this view, the loop starts making clockwise rotation. Well, we just said that when the loop itself is parallel to the field, the torque reaches its maximum value. So it starts from maximum torque. When it rotates, angle decreases, and eventually, when the loop is perpendicular to the field, torque is zero. What does it mean? Does it stop? No. It's like a pendulum. It keeps moving in opposite direction. However, now it slows down, and eventually it stops. When it happens, when does it happen? When does it stop? Well, when it makes exactly 180 degrees. So it's speeding up first, and then it's slowing down. What's happening next? Well, it should go back and forth, back and forth. Why this motor doesn't work like that? Why it moves always in the same direction? Well, the movie tells you, and the textbook tells you, there's a ring cut in half here, which changes the direction of the current in the loop, so the direction of the torque would be always the same.